So what's the big deal? Well, to give you a flavor for a formula. Yes?
So it's all about the charge balances, how it affects the pH and to what degree? So something with like just 2 protons to donate compared to 3?
So for pH, then you need to realize the proton, the free proton concentration. So that's what it is. Those expressions will be used in here for formulas to calculate the pH. Okay, so here's the flavor for you for this simple derivation. Okay, so let's use a weak acid. So HA, weak acid in water, then you can write the Ka, the product over reactant like that. Then highlight the HA. Okay, then write the mass balance expression, then it's going to be those not ionized versus those ionized, right? Then charge balance, the plus charge, one side, negative charge, the other side. Okay, so now you're going to substitute. From the mass balance equation, you're going to substitute the Ka expression. Okay, so the red one is the equivalence for the HA. Okay, so you substitute it by that. Okay, notice these two are the same thing. So instead of writing HA, then you write the equivalent. So there's an extension of the charge balance. The mass balance. Extension of the mass balance. So mathematically, then you can extract the common A minus, then you will write it like this. Okay, so for now, yes?
The reason you didn't keep the HA is because it had no charge?
No, this is just algebra. Mathematicians, they got all the time in the world, so they play around with that. But then chemists say that this is what equivalents are.
Right, because they,
Yeah.
okay.
Yeah, but then, this is just a mathematical game.
Okay.
Yeah, yeah. So, because it works, when you do substitution here and there, it works. So, based on reasoning. So, here, the base is, you're going to substitute the HA by its equivalence. Okay? And your mission is to end up with just one unknown, that is a H plus. So you don't want any other symbols in the formula. So you try to replace this and that. Okay, so you replace the HA with that, then you end up with that. So then the next thing is you employ the knowledge of charge balance. So extend it, okay, then here is that proton on the left, then it equal to the green A minus. So instead of writing the A minus, you write the equivalence of A minus. So the equivalence of A minus is right here. The A minus is right here. Okay, so A minus will be equal to this move to the left, right? So the left, you have CHA. And then this thing move to below it, then that's what it is, right? So below it, then this is the A minus. Then what about the hydroxide here? Instead of writing the hydroxide, then you write the equivalence, KW over H plus. So this shows you have just one X to solve for, right? So this is the way you prepare your solution. You know this numerical value, and this is a table value. So this is only X you solve for. Okay, so this is a universal formula that you can use for weak acid. Now, this is one weak acid, and this is contribution from your solvent. So I highlight the plus here. So the plus is a comparison. Then once you calculate that, then you can compare, compare the magnitude of this versus that. Then you may, in many cases, you can just ignore this guy, okay, and simply include that. Then here is another comparison. Then it depends on the relative ratio here. The Ka could be very small. Small will bring this to be a larger value. Then you can ignore the 1, okay? The 1 plus that. So you can ignore the 1 in many cases. Okay. Now notice this is weak acid dissolved in water. You get this outcome. Now you follow a similar derivation. If the weak acid mixed with a strong acid like HCl, then the total proton at equilibrium will be equal to the contribution from the weak acid plus the total contribution from your strong acid. So this one, replace that, okay? So HCl is strong and one proton, 100%, so you got to get that contribution. Okay, so this becomes a universal formula for whatever the Ka value is for your weak acid. Now what about if you have 2 weak acids? Then you go through a similar derivation. Then the total proton will be the contribution from 1 weak acid plus another weak acid. So each weak acid will give you this expression. Okay, and so on and so forth. So this is a universal formula for the case. Yes, Chris?
You don't add the Kw over protons like you did for the first weak acid?
Well, this is just 1 weak acid in water. And all these is going to be plus the Kw over H plus, but this contribution will be so much negligible once you get that in.
What about on the bottom one? If there are 2 weak acids, would you still include it, or when would you not include it?
Well, we'll have to look at the relative magnitude.
Yeah. So
Of
if it's
the Ka.
-4, then you add it, and if it's higher,
Well, we don't know yet until you plug that in numerical value, So if this over that is much larger than the 1, then you just neglect the 1. Yeah. Nonetheless, this is universal. If you have a computer program, or you can plug into your computer, all you need to know is the concentration of your 2 weak acids, experimental value, and then you know your table value for these 2. Then bingo, you get your H plus concentration.
And just ignoring the Kw over the H plus.
That's
So
right.
that works. Okay.
That's right. Yeah.
Okay.